In this recording, we compare the work and change in potential energy due to the gravitational force and due to the electrical force. Now we go back to the example of raising a brick from a position y sub I to a position y sub f. We said in that case that the work done by the gravitational force Fg is minus mg, and the change in gravitational potential energy is just the negative of that work, which is going to be plus mgh. Now, in the case of an electrical force, if we are going to bring a charge from very far away to a position RF away from this charge. Let me go back into the page to kind of get the monkey to move. Okay, there's the monkey bringing us the charge. Okay, now, so the charge was moved from very, very far away to a position RF away from the other charge. Now, what we know is that since both charges are positive, the charge that was moved by the monkey was subject to an electrical force. That electrical force is given by K Q1 Q2 over R squared in magnitude. Now the direction of that force is opposite to the direction of motion in this case, because both charges are positive and that charge is being repelled. So the force acting on it is going to always point in this direction. However, the closer we get to the large charge here, the larger is this force going to get, because R is going to get smaller. Now, when the object is at infinity, or very, very, very far away, what does that mean in terms of R? What it means is I'm going to have a very huge number here in the denominator that I'm going to square, meaning that the electrical force when we are very far away is going to be 0. And it's going to gradually increase till it gets to a value at this position here, where it is K Q1 Q2 over RF squared. Now, what's the work done by that electrical force? Okay, from here we see that the displacement and the force are in opposite direction, which means we are going to get a negative work, a minus KQ1 Q2 over RF. Okay, here I'm not showing you how we come up with the expression for that work. I'm just throwing it in. Mathematically, the only adequate way, in my opinion, to show how to come up with that work is to use calculus and to use what we call integration to be able to find it. I'm not going to do any hand waving to try to come up with this expression. I'm going to just throw it in. But since that force is not a constant force, it's not going to be there is not going to be an easy way to calculate it like we can calculate the work due to Fg here. By the way, as a side note, this equation, F is equal to mg, is applicable only at the surface of the Earth. However, if we decide to move an object very far away from the surface of the Earth, this equation is not applicable anymore, and this equation for the work done by the gravitational force does not work anymore, and actually it will look much more like the equations we have for the electrical force. So what we said, the work done by the electrical force is minus KQ1 Q2 over RF, and then using the fact that the change in potential energy should be equal to the negative of the work done by the conservative force, then that gives us this. The change in electrical potential energy is plus KQ1 Q2 over RF. Okay, it's a positive number here.